But there we go. Man, why do things change so much with these programs? All right, so let me start again. Mm. This is Darrell Lee Berry Jr. back with some more physics. I plan on working on some simple harmonic oscillator and infinite square well. I mentioned before that I'm taking quantum mechanics 2 right now. So basically, as is the case with many subjects, it's kind of like the same thing but harder, like the next level. So building upon the things that we did in Quantum 1, Quantum 2 is literally the second half of the same textbook. So Quantum 1, we did the first half of the textbook, and actually I don't know if we're going to finish the whole second half of the textbook. I don't recall. But we're starting on the second half of the textbook. And so in order to fully understand the Quantum 2, as you can imagine, you have to have a very full understanding of Quantum 1, which was not my best subject, right? It's not my top subject. So I ended up edging through with a B minus. It's not horrible, but it's definitely not my best subject. And so what I'll do is refresh myself on some of the basics. I plan on actually, I've scheduled a study group for Sunday, I believe, where I'll cover these topics as well. So also want to refresh myself for that and see how that goes. So I was thinking about trying to stream that, but it gets kind of complicated because we all students and uh, it is what's we call them school a class study group. So I won't do that, but uh, maybe I'll try to arrange something else I can stream. Like maybe if I do a Zoom one day, then I could just like stream my side and not stream the other side. So maybe look for that in the future. Maybe I'll hold a study group in on Zoom and stream it. Uh, but the idea is to get this down. So on 2 o'clock on Sunday, I'll help some people with it as well. Plus, I need to make sure to review it myself. So this would be a sort of, like I said, an impromptu, sort of more casual stream. I'm figuring it out myself as well, or refiguring it out. At one point, I knew it at least a little bit well enough. So change my setup a little bit so you can see the textbook at the same time. This is my textbook, the chapter on a simple harmonic oscillator. There's Church 4 in the textbook, chapter 2. And so you'll be able to see it out on the left side there. Maybe I can increase the size of it a little bit. And I'll be going through here, getting the inner workings of the simple harmonic oscillator again. By the way, something interesting. I found another picture of the Earth. So those who are regulars, I like my my pictures, my images. So I was just going through my folder and I found another picture of the Earth in my background. I'm certain this is a real one. There's just that one that I'm certain is a CGI one. I don't even remember where I got it from, but it's pretty cool. So I added that in the lineup of backgrounds that I have. So I think that's pretty cool. Nice view of Earth. Um, if somebody's watching, if you know where that pic came from, I mean, it seems like it could be a satellite photo. Like when I say satellite, I mean ISS type satellite. Um, but it could be just a regular satellite too. But it seems like an ISS photo to me, but I'm not sure. I thought that was pretty cool, so I added that in the lineup. Hopefully, y'all like the new look of the show. Haven't changed it too much, but changed it enough. Looks a little bit different, a little bit more uh atomized the different parts, so I can change things around a bit more. So here we go, simple harmonic oscillator. So let's see if I can uh relearn this quantum, the harmonic oscillator, right? So this was our textbook Griffith. The paradigm for a classical harmonic oscillator is a mass M attached to a spring of force constant K. The motion is governed by Hooke's law. So basically, um, something that got better at, but not so good at. You imagine you have a spring here. Let's say this is a box, a block or something like that, sitting on a table or whatnot. And the spring will have a certain tension to it. That's called K, the spring constant. And at rest, we can call that equilibrium. And what'll happen is if you tug on it or push on that oscillator, you'll end up coming out here. It'll end up squishing back here, but it'll go back and forth at a certain period. This could be called the amplitude. Uh, Frequency will be how fast it goes back and forth. And the uh, period t should be 1 over f if I recall, but or is at least proportional to 1 over f. So some of those details I'm forgetting. But as you can see, they give us the Hooke's law formula in the textbook. F equals negative kx equals m a. I'll add that in, which equals m, the second derivative of x over the second derivative over dt squared. So basically, this is the second derivative of x, which makes the acceleration. So ignoring friction, the solution of this would be for the value of x that solves this, x of t equals a sine omega t plus b cosine omega t, where omega is the angular frequency, which is square root of k over m, right? So this they call equation 2.42. So this is basically the classical analog to a quantum oscillator. So it's interesting that when you have like a small particle, let's say you have a molecule, you have an atom here, and you have an atom there, and they're connected to make a molecule. These molecules can oscillate back and forth, and it creates a situation similar to a simple harmonic oscillator. So this is one example of how these things can be oscillating back and forth, and you have a certain period of oscillation and a certain amplitude, and a lot of things can be modeled that way. Is actually very important, and it also gives the potential energy. See if it causes a potential energy or this potential. Yeah, potential energy equals Vx equals 1/2 kx squared. Now we have the force by Hooke's law. We have the potential energy, and the graph ends up being a parabola of the potential. So basically what we're looking at is potential V of x is looking like this. So if this is the center of the oscillator, I'll copy this image now. And again, we're still talking about a classical system, but a quantum system operates in a similar way. So if I was to sort of overlay these two, this is the comparison where when the mass is all the way to the right side, the potential is very high, it's going to be pulled back very hard. When it's in the center, potential is zero, and it just basically keeps on going. That's where the kinetic energy is maximum, right? So basically this is the maximum potential energy. Maximum potential energy. This is the maximum kinetic energy when it's going the fastest right in the center. And then when it gets to the other side, the potential energy is maximum, the kinetic energy is zero again, and it goes back and forth. right? So assuming no friction, then you would just have that going on infinitely. Of course, there's no such thing as a perfect harmonic oscillator. If you stretch it too far, the spring is going to break, and typically Hooke's law fails long before that point is reached. But practically any potential is approximately parabolic in the neighborhood of a local minimum. Formally, if we expand V of x in the Taylor series about the minimum, right, and subtract V of x, you can add a constant Vx with impunity since it doesn't change the force. Recognize that V prime of x naught equals 0, since x naught is a minimum. So again, they're talking about right here. That's the minimum right there at V naught. And drop the higher order terms with negligible as long as x minus x naught stays small. We get, so using the Taylor expansion, ignoring some of the terms, the lowest terms, the first term is 0. So think about this. So basically, the first term is the first derivative, so that basically deals with the slope. So one way of looking at it is the slope here is 0. That's the first derivative is 0 there. The slope here is maximum, so the first derivative, it has a very high, what slope here has a very high negative slope. So that's what we're looking at there. And did I copy something in part? Yeah. Let me erase this. So using a Taylor expansion, we have V of x is about equal to 1/2 the second derivative of x naught, x minus x naught squared, which describes a simple harmonic oscillator about point x over an effective string constant of v double prime xo. Basically, this is equivalent to k, how strong the spring is. That's why the simple harmonic oscillator is so important. Virtually any oscillatory motion is approximately simple harmonic, as long as the amplitude is small. So in other words, if we pull this mass out way out here, then the spring could break like they was saying, or it's just, even if the spring doesn't break or deform, the forcefulness of the motion will not have that simple periodic uh thing going to it. Also, Ayush, thanks for saying, thanks for dropping the line. I'm glad you're enjoying. If you have any questions, let me know. Happy to try to answer. Now, what we'll do is continue with the classical analog and work our way to the quantum reality and how it relates. And this is pointing out that basically, as long as we have a very small oscillation, you can imagine, I could pull this spring way out here, but you could imagine the spring it won't quite be that, you know, smooth curve when we get that far out. Therefore, only when it's a small amplitude down here is a simple harmonic. So we can say that in this example here, I'll just denote this as the amplitude that's simple harmonic, and I'll hear simple harmonic breaks. And is there any point I use that you'll like further clarification on, let me know that as well. Right? This is a pretty cool illustration by the book of what this looks like. Let me maximize this a bit. So basically what we have here is, and they'll explain the illustration later, Uh, what we have is a sort of valley, a lot of troughs and valleys of potentials, and we're basically picking out that one little spot that displays simple harmonic motion, which is similar to the drawing that I have here, where outside of that valley is no longer simple harmonic, but within that valley, it can be approximated as simple harmonic motion. So, which is pretty cool. You'd be surprised how much this stuff is applicable. Like, for instance, if you ever, everybody has, I'm sure, went through a door where the door has a sort of spring or a little device on it to where when the door closes, it slows it down. That's based upon springs and simple harmonic motion. Basically, it's a damped oscillator. So all of these things, even though it seems very pedantic and it's like you're just doing something just to do it almost, just like to have a physics problem. The fact is, understanding these things is very relevant to a lot of technologies that we have that we take for granted because we don't necessarily know the physics behind everything. But but if people didn't know the physics behind this stuff and was not able to exploit that physics and maximize the what's going on with these physics properties, a lot of technologies that we have and take for granted we wouldn't have. So let me go ahead and place this again, and we'll keep going. Let me check, by the way. I don't think I heard anybody join Discord, but I'm in Discord as well. I'm usually in Discord when I'm streaming. In case anybody does pop in, I figure in the future, after the channel builds up some more, we might have some people in Zoom live as well, doing like uh, live Q&A and discussion. But let's continue. Okay, so now we get into the quantum. All right, we have this as the classical, and this is the potential energy. We have Vx equals 1/2 V double prime, that's a second derivative, using the Taylor expansion at the central part, x minus x naught squared, because that's a second derivative. Now we have the quantum potential, which is Vx equals 1/2 m for the mass of the subatomic particle, omegas for the um, frequency, and x squared is for the position x. This is equation 2.44. It's customary to eliminate the spring constant in favor of the classical frequency using equation 2.42. As we've seen, it suffices to solve the time-independent Schrodinger equation. All right. So as a bit of a review, and I can see if I can deduce this without scrolling back to the time-independent Schrodinger equation. Basically, we're taking a Schrodinger equation, we're extracting the time component. So now we're just looking at the space component of the Schrodinger equation. So if I was to write this out, we can say that negative h bar squared over 2m, uh, second derivative, second partial derivative of psi, and psi is the wave function of the subatomic particle, x squared, and actually let me write it in the disjointed form, plus Vx psi equals E psi. So basically this component here is the Hamiltonian. It is the part of the equation that gives us the energy. You could also say this. So this Hamiltonian, this is one of the forms it takes, this entire thing here. When the Hamiltonian acts upon the wave function of a subatomic particle, it outputs the energy of that subatomic particle. So that's where that comes from. Uh, so now it's just in this case, since we're dealing with a simple harmonic oscillator, the potential is this. So all they did was plug that in, and now we have negative h bar squared over 2m partial squared over partial x squared plus, I'm going to input that, 1/2 m omega squared x squared psi equals E psi, because the uh, Hamiltonian acting upon psi gives us the energy related to that psi. And in equation 2.45, they simply distributed that. We have negative h bar squared over 2m partial squared psi over partial x squared plus 1/2 m omega squared x squared psi equals E psi. And now we have equation 2.45. In the literature, you will find two entirely different approaches to this problem. The first is straightforward root 4 solution to the differential equation using the power series method. It has the virtue that the same strategy can be applied to many other potentials. In fact, we'll use it in chapter 4 to treat the hydrogen atom. Okay, so that's important. The second is a diabolically clever algebraic technique using so-called ladder operators. And they're going to show the ladder first, but I'm going to move to the power series simply because um, so we have basically three primary, I guess I can't say primary, but they stick out to me, types of systems, quantum systems that we'll be discussing in quantum 2. So one is the triple harmonic oscillator or the harmonic oscillator, which we're discussing now, which is basically the oscillation of subatomic particles with small amplitudes. We have the infinite square wheel, which I may not have time to get to. I spoke about it before, but I may come back and do that one at a time, or maybe let y'all look at one of the previous videos. I'm sure I spoke about that one before, and I pretty have a pretty good handle on the simple on the infinite square wheel. And then we have the hydrogen atom, which is a very important one, and I think the only one we can uh, solve very fully. I'm going to skip the algebraic method, and I'm going to go straight to the power series, since that'll prepare me for the uh, hydrogen atom as well, which that reminds me I need to look at too. So I'm skipping all of this, skipping. All right, all right. So we're going to solve it with the power series method, right? So this is from 2.3.2 analytic. Method. We have, we still have this equation, equation 2.45. Looks like they just rewrote it and called it 2.71. Do and solve it directly by the power series method. Things look a little cleaner if we introduce a dimensionless variable. All right. So basically, um, right. So this is something to make things a bit easier. Forget all about this. We're going to define this symbol as the square root of the mass of the particle, the frequency of oscillation over h bar times x and h bar equals the Planck constant over 2 pi. So used to drawing a bar. So that's that. So this is 2.72. In terms of E, the Schrodinger equation reads, all right, so let's look at this. So they're saying that partial squared psi over partial, forgot what that thing is called, Z, I think, squared, I'll just call it Z, is Z squared minus K psi. Right, so let's see how this works. We'll keep going. So I'm not seeing right offhand how to integrate that immediately into the equation. Um, but hopefully they'll illuminate that as we go. All right, we have that, and K is defined as 2e over h bar omega. This is 2.74. I'm going to have to get a better understanding of uh, how this z fits into this equation here. Yeah, okay. So this equation here, which is 2.71, maybe I'm thinking about it incorrectly. I'm glad I'm reviewing this. So I think right now we're just defining stuff. We're defining what these things are so we can plug them in later. But I see that they, in 2.73, we did get a result by taking a second derivative of psi with respect to that. I see. I see. So what they're doing is they're defining, uh, I see. So basically what they're doing is they're taking this z and they're defining it not to put into the Schrodinger equation itself, but to put into the solution for the Schrodinger equation, such that when we take the second derivative of the Schrodinger equation, it outputs this. So the idea is that the Schrodinger equation is a second order differential equation. So differential equations are equations that it takes functions to solve. So like x double dot equals a squared x. And we need to find what function will solve this equation. So if x equals, let's say, e to the kx, say x of t, or no, f of x, there we go. If f of x equals e to the kx, I'm not sure the best way to write this. What's the best way to write x? I don't know, right? This is t. So x of t equals e to the kt, right? So x prime of t would be ke to the kt, and x double prime of t, or I should say double dot of t, would be k squared e the kt. So we see that if x of t equals e to the kt, we can solve this differential equation, and that's what's going on here. So basically what we're doing is we're defining a z such that when I take the second derivative of the function, instead of outputting a squared, we output this. All right, so that's what it seems like is going on here. So we're defining z that we're going to place into the solution for the equation. Our problem is to solve equation 2.73 and in the process obtain the allowed values of k and hence e. To begin with, note that at very large z, which is to say at very large x, z squared completely dominates over the constant k. So in this regime, the second derivative of psi is similar to z squared psi, because z squared will be so big that k will be pretty much zero. So and essentially we end up with an equation like this Mach equation, if we define it this way. All right. So they're saying that, and this is fitting what I was surmising was going to happen. So they're saying that psi of z, after we plug z in, is approximately ae to the negative z squared over 2 plus be. And thank y'all for watching who's joined. Be sure to drop a line if you hear. Ask any questions if anything comes up that you'd like clarification on. And we'll keep it going. I guess I'll be here for another 45 minutes or uh, more or less. I'll see if I can complete this thing. We have plus z squared over 2. This is equation 2.76. So as I surmise, we're defining z such that we can output what we want. And if z is very big, so if z is much bigger than k, then we can say that psi double dot equals z squared psi, because k is relatively smaller. Be sure to drop a line, ask any questions if you like, anything you'd like clarifications on. And right now I'm basically reviewing the simple harmonic, the harmonic, quantum harmonic oscillator, and to rebuild my foundation for quantum mechanics 2, which is basically taking these things a step farther. But right now we're looking at the basic case of the quantum harmonic oscillator. Like if you have a molecule where the atoms are oscillating a very small amount in a consistent way, for those who just joined. All right. So now we have this equation that z will solve in the equation how we defined it by taking a second derivative, right? We have the b term is clearly not normalizable. It blows up as x goes to infinity. The physically acceptable solution then have the asymptotic form. So in other words, what they're saying is that um, x is a part of z as we defined it. So x is here, and maybe it might make it better to write x in the front. So x is being multiplied by this thing to make z. So if x is really big, z will be really big. And the bigger z gets, this positive exponential will then be squared and that'll get even bigger. And eventually, if you study the particle very far away, this is going to equal infinity, which is impossible. Like a particle doesn't have an infinitely big wave function. And Silver Phoenix Rising says, I never learned differential equations, so this is interesting. Awesome. I'm glad you're finding it interesting, Silver. If you have any further questions about it, let me know. I'll be happy to go into a bit more detail. A bit earlier, I gave this simple mock differential equation, which is how we basically found a function that solves this differential equation, just like how we might find, a number to solve uh, 2x equals 4. You solve for x with another number, obviously 2 here. In the same way, a differential equation, we find the function that solves for x. And that function is a solution to the differential equation, which could actually get pretty complicated. So maybe what I'll do, Silver, one day I'll do a video on differential equations. I actually very much like our textbook for my differential equation class. It was my best class. I made a B. The professor didn't have a plus or minus system. He said if he did, I would have made a B plus. Well, he just simplified his grades and just made it A, B, C, D. So I ended up getting a B, which is not bad, right? But there's still some room for learning I can do on differential equations. But have enough of it. Yeah. So look for that. I'll schedule that. It might be in a few months, as I'll focus on the topics, which unfortunately a lot of these topics use differential equations. But probably on spring break, when I have some time to not have to study the subjects, I may make one. I have to break that textbook out. I think it'd be good to break that textbook out and get some. Like I made this example up. It's a good enough example. But the differential equation can get pretty complicated. So I'll break out my differential equation textbook and actually do some go through it a bit, just like I'm doing here with this quantum book. And you'll see it on the schedule. So awesome. So we'll keep going with this. Now, as we were saying, this will go to infinity as x, basically as s goes to infinity, this will go to infinity. And basically what happens is if you have a quantum particle in a potential, at infinity, that potential is going to go, the energy is going to go to zero, basically. So like the particle is going to be contained to some extent, it's my understanding. So if that blows up to infinity, then it doesn't seem to be a physically uh, applicable system. Therefore, we end up with psi of z equals something in the front here and e to the negative z squared over 2. And this is at large z. So if z is large, where it dominates this equation here and makes k inapplicable, only the negative exponential works so that it doesn't go to infinity, right? So they say this suggests that we peel off the exponential part. So we have psi of z, and this thing is kind of hard to draw, but I'll get you better at drawing it over time, I'm sure, equals h z e negative v squared over 2. So basically, it's saying that this is what fills that spot there, right? In hopes that what remains, hz, is a simpler functional form inside itself. All right. So we did all that in hopes that we can define z in such a way that we can solve a different equation. This is different, of course, than our original wave function, but hopefully it's going to be a simpler function that contains all the information about the particle, but in a simpler form that we can solve more easily, right? All right, so not about to get extra on us. So we're going to take this equation here and we're going to differentiate it. So basically, we want to take the derivative of this equation. So we're going to say d psi over dz equals, let's see if I can take the derivative of this myself without looking at the textbook answer and just writing it. May get it wrong. Let's see what we have here. We have h as a function of z, and we have e as a function of z. It tells me we have to do the power rule. So I would do h prime of z times e to the negative z squared over 2 plus h z, and we're going to have to take the derivative of the exponent. So that's going to be negative 2z over 2 e negative z squared over 2. So if I did that properly, this will cancel, leaving just negative z. So I would say h prime of z e negative z squared over 2 minus, to pull the minus out, h of z. Um, we have z e negative z squared over 2. And to simplify it, I'll extract the exponential. We'll have h prime of z minus z h of z, and all times e to the negative z squared over 2. All right, so let's see if I got that incorrect somehow. So looking at the book, looks like that's what they have. Just notice the book often, and that's why I tried to simplify it a bit, but you notice the book uh, often simplifies things farther. Sometimes it seems like they're just being complicated, but a lot of times later you can tell the difference what they did. Uh, but basically, they wrote my h prime of z. They just actually wrote the derivative out, and they used the parentheses instead. So they have dh over dz. So that's the same thing, minus z, and instead of writing the h of z, they just wrote the h. A lot of times I write the h of z to remind myself as a function, because a lot of times I forget that, the close parentheses, and then everything else is the same. So it looks like I got that right. So now some good practice on differentiating. All right, so there we go. Put this back. So basically I just rewrote it in the form that the book has it. So that's the same thing. This is the same thing. It just didn't write that. And of course, the last thing is exactly the same, right? Oh, and oh my gosh, it did a second derivative as well. Should have known I wasn't off the hook that easy. All right, so we have d squared psi over d, well, write this a bit smoother, d squared psi over d z squared equals, okay, here we go. Now this gets a bit more complicated because now we have this component and this component in our derivative. So we still have a product rule, but this also has two components in itself. Basically, you have two components for our product rule, and you have the two z components up in here. Because remember that this is h of z, which is why I often write it so that I don't forget. So let me put this back the way I had it. Erase the wrong thing. Before I forget that that is a function as well and don't do it properly. Right. We're going to take the second derivative of this. They equal the same thing, but this makes more sense to me, right? So product rule, I'm going to take the derivative of the first one and the second one. So we have h double prime of z minus, and now we have a product rule inside there. We have uh, e, make a big parentheses here. We have h z, because of the derivative of the z just makes that 1 plus z h prime of z. Right? And then we have e to the negative z squared over 2. So that's the first half of the derivative. Now we got to take the second half. So that's plus h prime z minus z h z. So I'm rewriting that first part since now I'm not taking the derivative of that part. And then we have what? That was negative 2z over 2. So there's negative z and e to the negative z squared over 2. Right. So that should be the full derivative. So, oh, and Nicholas says, Silver says, taking algebra in high school is definitely helping me follow along. Awesome. Yeah, so I mean, a lot of it is algebra. It just basically that's the interesting thing about it. You build upon what you know, so it's constantly building upon, building upon, building upon, which is cool. So a lot of the things we learn in high school doesn't seem like it's going to matter, but it does. And Nicholas says Planck flux equals fundamental flux speed constant equals bisector reflector density, local Planck flux, right? So I'm not sure what Nicholas was referring to, but thanks for sharing. Uh, see, there's a GR. Maybe you mean, I don't know if you mean general relativity. Uh, but awesome. Thanks for dropping a line. Anybody else here, be sure to drop a line so I know, well, I see you there, but drop a line. So some interaction makes it more fun. Let's see here. Got about 25 more minutes. I'll hold on and see how far I get in this. But first, let me make sure I got this derivative right. So I'm going to try to combine these. Let's see here. We have h. I'm going to drop the z now since I took all the derivatives. H double prime minus h minus z h prime, right? I was thinking about trying to just drop that all in at the same time, but let me actually break it into two steps. Z squared over 2. Now what I'm going to do here, I'm going to distribute this, try to make this simpler, right? So this is going to be plus minus z h prime plus, so this is going to be z squared h and still e to the negative z squared over 2. So all I did was just distribute this negative here. So that became negative negative. And I distributed that negative nz. So we have z bringing that negative and then z squared, making that positive because it was already negative. Let's try to extract the z one more time because the book has the z on the outside. And I can see if I got it correct. H double prime minus h minus z h prime. I'm going to minus v h prime plus z squared h, and then we have e to the negative z squared over 2 on the outside. Let's see if any of this cancels. I don't think it does. So we have h double prime minus h minus 2 z h prime plus z squared h, and then e to the negative z squared over 2. So let's see if I got that right. Let's see here. So, and of course, they have to be difficult. You have to simplify it a bit more than I did. Let's see what they did. I can try to do this one more thing for see if I can maybe adjust the size of these things so you can see what I'm talking about. So if we look at the book answer is this line here. See that? That you can see. That's the book answer right there. And this is my answer here. So it looks like it's right, except they made one more simplification. Let's look at this. So basically, we're going to write it the h double prime as h over the z squared, and so that's this part here. And we're going to minus the 2d. We're going to write that as dh over dz. That's this part here. And what we're going to do with these parts here is combine them into one thing. So we're going to say plus z squared minus 1 and put the h on the outside. So basically this h that I have here, I put on the outside from both of these. And that leaves a negative 1 here, which is there. And there's the z squared by itself, which is there. And we distribute that, we get the same thing. So then that might have looked complicated, but we can see that that is the correct answer for taking this derivative. I have one more parentheses to put. There's a parentheses out here. Then we have e to the negative z squared over 2 multiplied by everything. So that's what that is. All right. Let's take a look at this and see where they're leading us to. So obviously, they're leading us to a solution to the simple harmonic, at least the harmonic oscillator. So we shall see how close we get to that. Right, and Nick says photon is a spin orientation wave. Everything is united through the bisector reflection of the inverse directional momentum. I think on fundamental flush. So, Nicholas, what are you doing? Like, what is your intention? Like, is it are these things that you really believe or have evidence for, or are you just like trolling in the chat? Like, what would you say is going on here? Because it seems like you're just rambling a bunch of words together. So, why don't you let me know like what's going on? Uh, you mean you're explaining what I'm doing right now, or when you say you're explaining the whole thing, what are you saying you're explaining? Great, man. So you seem like you're sort of just filling the chat with nonsense. It seems like nonsense. What you can do if you think you're actually saying something, uh, you can let me know and you can come on and present what you have to say. But I mean, what you're doing now is not. I don't think it's helpful. So try to hold that, and what you can do if you really think that you have some kind of understanding that you're explaining. Uh, Let me know what Saturday you want to come on, and you can come on Saturday and you can present what you want to present, and I can question it. Uh, uh, I see. Well, thank you for letting us know, but it's not really helpful. I don't think you're really hoping the conversation right now. So right now I'm uh reviewing the solution according to the textbook. So if you think it's wrong and you know better than all of these physicists, then congratulations. Maybe write up. Well, that's fine. So yeah. So but what I'm going to do is go ahead and go through this because these are the people who made the inventions you're using right now. So unless you can point to well, then point us to the technologies that you have that you've invented better, and point us to the laws of nature that you discovered better, and all of that stuff. Otherwise, right now you're just talking, and it's not really helping. So yeah. So whenever you can point us to all the technologies and inventions you made that are better than everything that we use somehow, then we'll accept that you're better when you actually produce things that's better. But just rambling doesn't mean you know better. It just means you're rambling. You have to actually demonstrate that it's better by real effects in the world, right? Not just a whole bunch of words that you're rambling, but technologies, laws of nature that you've discovered that are better, that you could demonstrate are better. All right, so let's keep on going. Uh, Now, so we have these derivatives, and and uh, so now the Schrodinger equation becomes. So this is the second derivative. All right. So let's rewrite the Schrodinger equation again. So we have negative h bar squared over 2m partial derivative over partial x squared plus vx psi equals e psi, right? And the psi that we're using is going to be this. Right? So this is the psi that we decided upon. I think I'm gonna have to ask my professor. I don't quite recall how we decided on this to be psi. Like I know we just defined it, but it seems like there's some detail that's not. Uh, well, like I said, man, if you really understand better, let me know what day you want to come on, and you could explain it. I started off with that. But it's just right now, this is not helping. I could just let you know from my perspective what you're saying just doesn't make sense. So this seems like a bunch of rambling words. That's what it seems like. If I'm wrong, let me know what Saturday you want to come on to the show, and I can give you the time to present. You can present what you want to present, and show us how you're right and better, and that's fine with me. Uh, then just let me know what Saturday you want to come on, and then we can bring you on. Uh, Well, the reason why I didn't want to say now is because I mean, I'll be leaving in a bit, and I actually want to keep this focus on quantum mechanics. I just don't want him flooding the chat when if other people actually have valid questions. Well, like I said, Nicholas, just let me know what Saturday you want to come on, and instead of putting the knowledge that you have that's better than all the quantum physicists and stuff in this chat, you can come on and actually explain it and show people and make a presentation and all of that stuff. So if I don't know better, then it's fine. You come on and show us, but I'm just letting you know that right now what you're doing is putting all in the live chat is not helpful. It's not really helpful, right? So let me keep on going. So this is the side that we're doing. And basically what we're saying is if we plug this in for psi, my understanding is we get this out. So I already took the second derivative, I got that. I'm not going to go ahead and work through the whole thing. So basically what we're doing is negative h bar squared over 2m. Uh, second derivative psi z over second, is that z? Guess it has to be z squared plus uh, we have 1/2 m omega x z equals e psi. Yeah, but you notice, by the way, Silver, he hasn't given a date yet. You keep saying what you can do. Just give a date. Just let me know what Saturday you want to come on. My show is 8 p.m. Central Time, and you can squash this. But the very fact that you keep wanting to talk in live chat rather than actually present your position lets me know that on some level you must know that what you're saying is nonsense, right? Um, but again, if I'm wrong, just let me know what Saturday you want to come on, and we can make that happen, right? Yeah, you could come on tomorrow. So 8 p.m. Central Time tomorrow. Just meet me on Discord, and I could just move the show I have planned back. So tomorrow, 8 p.m. Central Time. Right now, it's 10:48 p.m. Central Time. Uh, I thought you just type anytime. Can I go tomorrow? Okay, so just let me know the actual date. When you ask any date I can go tomorrow, you were not serious about that. So why don't you just give me an actual date, Nicholas? So I could put it on the 18th. Yeah, so tomorrow. So right now it's 10:49 p.m. Central Time. So can you be here 3 hours earlier from now? Okay, so 3 hours earlier from now, just join the Discord. Uh, awesome. Thanks for clarifying, Silver. So tomorrow at 3 hours earlier from now, you see the Discord uh, uh, right under my image right there. You could join our Discord there, and then you'll be in the Discord, and we could go on stage, and you could present. And keep in mind, I'm going to challenge you as well. So I'll give you some time to present what you're going to present, and then I'll challenge your what you're presenting against what I understand of uh of you know established science, right? So what you're saying is really better if you'll be able to hold up to that. Awesome. So I'll see you tomorrow. Again, tomorrow, 3 hours earlier from now. So whatever time it is by you now, 3 hours into the past, I'll see you on Discord, and then we'll get started. Awesome. Sounds good. So and I'll wrap up again over the next 10 minutes. Uh, we got pretty much to the Schrodinger equation, which is here. So seems like a good place to stop. There's still a lot of details I'm going to have to look into. As you can see, let me put the textbook a bit a bit bigger. So one moment here. He said he'll be here. I mean, if he doesn't show, I might just silence him if he's just gonna keep filling up the chat and not showing. I might just, because that's what I think. I figured this would happen because I know in the past I dealt with these flat earthers a lot, so there's probably a lot of conspiracy conspiracy theories and stuff that'll still be coming for a while. But like I said, I'll just do the same thing for everybody. If you know better, come on and show us. Otherwise, I don't see any reason to let somebody just keep filling up the chat. So, but he said he'll be here tomorrow, so we'll look for him tomorrow and we'll do that. But this is what we're going to be heading towards. So we got to here to what I'll do uh uh is maybe come tomorrow in the daytime sometime. So like I'll be working tonight. So actually I have all night to work on stuff. Even though I plan on uh uh focusing on the coding that I'm gonna do for my we can go ahead and I'll stop the what's it called, I'm sure. But yeah, so I work as a student security coordinator, usually work overnight. And so tonight is one of the nights I work. So during downtime, usually I try to study or something like that. So during downtime today, I actually have some coding to do on my research. So uh, but I have to make sure I understand this in more detail for the quantum two stuff. So I'll make sure to study some of that too. So maybe I'll do an impromptu stream sometime in the daytime tomorrow if I don't go to sleep. Uh, uh, and we'll see if I can fit that in. But also, Nick, so I'll see you tomorrow, 3 hours earlier from now, and I'll give you some time to present your position, and then I'll challenge your position after that. And I may still either the stream that I had planned with gravitation, either I'll still do it an hour before, an hour later, or I'll just push it back to the next week. So we'll see out of the way. It's awesome. Thanks for showing Silver. Thanks for dropping a line. Thanks for showing Nick. I'll see you tomorrow. And thanks to all who dropped by and watched. Uh, so again, that's tomorrow. Thanks, Silver. Awesome. And again, Nick, that's tomorrow, 3 hours earlier from now, right? Awesome. We'll talk about that tomorrow, Nick. Sounds good. So everybody, thanks for joining. It was good seeing y'all. Like and subscribe if you haven't. I'll be on tomorrow for at some other time for some quantum stuff, maybe some gravity stuff. But tomorrow at 8, it'll be Nick, and we'll go into what he's talking about. I'll set the stream for that right now, so you'll be able to see it show up momentarily. Everybody have a good night.